that he did with one of our biochemistry professors, Peter Anderson.
Hello everyone. Before I begin, I would like to thank Dr. Peter Anderson for making this project possible. Anyways, my name is Aryan, and today I'll be presenting about alternatives to rifampin in multi-drug-resistant tuberculosis. Now, doctors, researchers, as well as pharmacists can all agree that there's one major problem when it comes to drug development. And that problem is resistance. Now, just as us humans and animals evolved using natural selection to adapt to their environment, unfortunately, viruses and bacteria do the same. And that becomes rather problematic for us because the antibiotics and the medications we create to combat these viruses are simply rendered ineffective. My project focuses on a specific disease, that disease being tuberculosis, and very specifically, multi-drug-resistant tuberculosis. Now, this is a pretty huge problem. According to the World Health Organization in 2023, multi-drug-resistant tuberculosis affects nearly 500,000 people annually. And this problem will only grow larger. As we can see here, currently, this is the map of the global TB hotspots. As you can see, they're mainly centered around developing countries. Now, that being said, this is because tuberculosis, once the symptoms are onset, it is particularly difficult to cure. Much more multi-drug-resistant tuberculosis. Now, when I talk about multi-drug-resistant tuberculosis, I mean tuberculosis strains that are resistant to both rifampin and isoniazid. Now, the problem with this whole entire situation is that with isoniazid, we have easy to procure alternatives. However, when we look at rifampin, the alternatives require a lot of medical oversight and a lot of replacements. This simply is not a viable option for developing countries. So looking exactly as to why rifampin resistance is caused, the short answer is mutations in RNA polymerase enzyme. In layman terms, what this means is rifampin, being an inhibitor, wants to bind to tuberculosis, and the changes in tuberculosis structure becomes inherently problematic when rifampin tries to bind to it. Looking in more detail, basically, rifampin binds to the beta subunit of the tuberculosis bacterium. This is a place that's near the active site, and what this does is it stabilizes a specific conformation of tuberculosis. That conformation stops the formation of the first phosphodiester bond, which prevents RNA synthesis, which prevents the creation of proteins, and which furthermore prevents tuberculosis from reproducing. This eventually causes tuberculosis to die off. However, mutations in the RPOP gene basically affects the binding site, causing rifampin to be unable to bind to tuberculosis. What this causes is in the next generation of tuberculosis, we essentially have rifampin resistance. And this image is just a brief explanation as to how this works. Now, we do have a solution to this already that's present, and that's to use alternative drugs, a lot of therapy in order to reach the solution we want. And like I said previously, this solution simply doesn't work for developing countries. So the solution Dr. Anderson and I came up is to create an alternative drug to rifampin. And these are our lead compounds, aka our final products. Now, a lead compound doesn't mean we can immediately start using them. These are a lead to our experimentation, and we need a little bit more research on top of this to sort of get to know these compounds a bit better. That being said, these are my two lead compounds, ligand 118 and ligand 124. The formula is right there. These are the structures. Moving further, as you can see here, this is the compounds performing their duty within the tuberculosis compound. See how wonderfully they fit. Beautiful molecule, and that's basically my final product. Now let me explain to you how we reached these final products and the considerations that went into this. The first thing what we did was we found a rifampin-resistant tuberculosis strain. Now this is clearly important because we need to know what the product looks like and what we are trying to tackle. Now for this, we used a substitute, E. coli, rather than Mycobacterium tuberculosis. And this is an apt replacement because they both express the same antigens. But we used E. coli for two particular reasons. Number one, it's simply easier to manipulate. And number two, in a more bio sort of research, when you go into lab testing, it's definitely a safer alternative than testing with Mycobacterium tuberculosis. Remember, they express the same antigens, so it makes it an apt replacement. Moving further, from there, we started designing the plausible compound. As you can see here, this red circle right there, that's where we want the target to bind to. And we basically calculated these binding coordinates as that value. And that's 113.7 for X, 27.6 for Y, and negative 11.4 for Z. From there, we used an E3D-led web server. What this did was it took a already existing FDA compound and then used molecular mechanics algorithms to essentially derive more compounds that fit to the binding compound with the molecule we have in mind. So with that, we were able to produce 510 drugs, out of which only 211 of them were unique. Moving further, we then evaluated these lead compounds that came. Our first criterion was binding affinity. It's important we measure binding affinity because we want to have the ligand bind to the compound. And so what we essentially get here is we base this on a KD value, ligand dissociation constant, and our value threshold was 100 nanometer, which according to various sources of literature is an ideal number to see if the drug is effective. I have sourced at the end, of course, so you can see the sources for that. But this is basically the KD value we evaluate on that. We can use this, Autodoc Vina and X-score to average the calculation in order for that. And out of that, we were only able to get 35 out of 211 unique ligands to bind to the target protein with high binding affinity. This overall tells us our basic concept and thinking. As you can see, ligand 21, binding affinity of 200 nanometers, fail. Ligand 45, 0.8 nanomolars, pass. And of course, our two that passed in the end, 118 and 124, 61, 67 pass. And when we look at rifampin, however, we have 182, which is a fail. That's the basis of our experiment or the whole entire process of the project, because rifampin simply does not bind to a rifampin-resistant molecule. The second test we did was the ADMET test. ADMET stands for absorption, distribution, metabolism, excretion, and toxicity. Now we looked at two specific things, GI absorbivity and toxicity. GI absorbivity is basically how well it works in a pill format. And this is particularly important because our target is developing countries. And when we look at needles, it has many bioethical concerns, especially with the reuse of needles and the overall fear that needles have. That being said, we also looked at toxicity. We simply do not want to poison our patients. So we stuck with toxicity, and our ratings were for high rating and the class 4 and above. We calculated this via Swiss ADME and Protox 3.0, and only 2 out of our 35 unique ligands were able to pass all these baselines, ligand 118 and 124. This once again is our thinking that occurred. As you can see, ligand 21 and 45 simply failed. They did not pass both tests, but ligand 118 and 124 passed, as well as rifampin, because rifampin obviously was an FDA approved drug, has been in action, has passed all the baselines. So once again, these are the final compounds we came up with. But before we can start experimenting, I do have some further considerations I want to make. And those considerations are, I first want to look at the resistant and mutation pathways. Now, obviously, at one point, my compounds will eventually be resistant, and tuberculosis will be resistant to them. And so it's important to look at these and check if they can maintain efficacy, as well as I want to do some further testing, maybe validate the lead compounds with more tests, and possibly simulate the drug in action with more computational models. Now, in summary, let's cover what we learned today. We know that tuberculosis is already a pretty big problem, much less MDR tuberculosis. That being said, with affecting over 500,000 people annually, it's very important that we figure out a solution. We boiled down the problem to the fact that we don't have alternatives to rifampin, and my solution to that, and Dr. Anderson's help, we created lead compounds as alternatives. These are my sources. Thank you for listening, and I'll be taking questions now.